So in this video, we're going to prove the theorem that every principal ideal domain is a unique factorization domain. In preparation for this theorem, we've proved two lemmas. The first is, if you have an irreducible and a principal ideal domain that divides a product, then that irreducible has to divide a single term in the product. And then we have also had the ascending chain condition, which says that there cannot be a strictly increasing chain of ideals that's infinite in a principal ideal domain. Okay, so let's prove the theorem. I want to take A to be in my principal ideal domain to be a non-zero, non-unit. The goal is to take A and write it as a product of irreducibles. That's what we have in a unique factorization domain. We have the ability to take any element and write it as a product of irreducibles or primes. So imagine integers can be written as a product of primes. If A is already irreducible, great, I'm done. So if A is irreducible, then great. I'm done. If not, then here's the idea. If A is not irreducible, then A can be written as A1 times A2 for non-units A1, A2. If A1 and A2 are irreducibles, then I've achieved my goal. I've written A as a product of irreducibles. If not, then I'm going to break A1 and A2 up into pieces and see if I get irreducibles. Then I'm going to keep doing this process. So I'm going to take A2, break it into hopefully two irreducibles, break those up, and eventually find irreducibles. Here are the details. Let's say if A2 is not irreducible, then take A2 and write it as A3, A4. A3 and A4 are not units either. I'm not going to write that down from here on out, but I'm going to know that if I'm going to have a irreducible, if A2 is not irreducible, then it could be written as a product of two things, neither one are units. So then what we see is now we have A is A1, A3, A4. Now if A4 is not irreducible, then A4 is A5 times A6 for non-units. Then we see A1 is A1, A3, A5, A6. I want to repeat this process until eventually I'm going to get A as some A prime. A prime will be the odd subscripted terms that I'm writing down here, times P, where P is irreducible. So I'm saying you keep breaking up this last term until you find an irreducible. And you might say, well, how do I know I'll be able to eventually find an irreducible? Why can't I just keep going down and down and down forever, never actually landing on an irreducible? Well, if this process doesn't terminate, then what we have is the ideal generated by A is strictly contained in the ideal generated by A2, which is strictly contained in the ideal generated by A4, and so on. that would be a strictly increasing chain of ideals that can't happen in a PID. Let's verify that we actually do have a strictly increasing chain of ideals. Well, first notice that this is a chain of ideals. A2 times A1 is A. So that means A is definitely in the ideal generated by A2. So I get containment this way. Why can't I get these two ideals to be equal? Well, if let's say that I do get equals, these ideals are actually the same, then that would mean that A2 was in the ideal generated by A1. So A2 could be written as A times some B, if the ideals were equal. And if that happened, then I can go back to this equation and I could say A is equal to A1 times AB, and I'm in a principal ideal domain, which itself is an integral domain, and in an integral domain, you could do cancellation. The cancellation laws hold. So I can cancel these A's, and I would get 1 is A1B, which can't happen because then A1 would be a unit. A1 would divide 1. A1 would have a multiplicative inverse, which does not happen. So that mini verification justifies why I actually have a strictly increasing chain of ideals, which can't happen. So back to the proof, what we have now is that we could take A and write it as A prime times an irreducible. Then we could do the same thing with A prime. So then we see that A is equal to A prime times an irreducible. We could break up A prime. Let me call that actually P1. We could break up A prime into A double prime times an irreducible P2 times P1, and we can keep breaking this up until we get a product of irreducibles. For the same reason that our original process must terminate, this process must terminate too. So we keep doing this until we eventually get Pn times Pn minus 1 down to P2, P1, all irreducibles. So that proves that I could take a non-zero non-unit element and write it as a product of irreducibles. But this is a unique factorization domain, meaning there's some sort of uniqueness uniqueness property as well. So now suppose that A is a product P1 through Pn, but also Q1 through Qm, where everything is irreducible. So suppose I could write A as a product of irreducibles in two different ways. I need to show that these two different ways really aren't that different at all. The only difference is maybe I've shuffled around the terms and maybe I've multiplied by some units here and there, but really it's the same expression. Well, now we're going to use lemma 1. We haven't used this one yet. We've only used the ascending chain condition in our argument so far. This condition says that if a prime divides a product, then it must divide a single term in the product. So then P1 divides this product, so therefore P1 divides the Q product. P1 is an irreducible, therefore by the lemma, it must divide a single term in the product. So I'm going to say P divides Qi for some I. Now what that means is that P1 times some U has to equal QI. That's the definition of divides. But Q1 is an irreducible, meaning that U has to be a unit. So U is a unit, and both sides of, U is a unit, and therefore P1 and QI are associates. Now I'm in a principal ideal domain, which is an integral domain, and in an integral domain you can cancel. So I'm going to take this expression for A, multiply both sides by U, so multiply U on both sides, and then I get P1U is QI, so I get a QI over here, and of course I have a QI in this product. I can cancel those, and we get that P2 through Pn is equal to U Q1, Qi minus 1, Qi plus 1, because there's no Qi term, I canceled that out, up to Qm. Then you just repeat this process and continue inductively. So I'm going to write continue inductively. Look at P2. P2 has to divide one other Qj. They're only differing by a unit, so they're associates. You can cancel them out and then repeat the process. So eventually you'll cancel everything out and just be left with 1 on both sides. So this implies n has to be m, and it implies that you've really just rearranged the terms. So that's the end of the proof of the theorem that every PID is a UFD. So there was a lot of details to check there, but the main idea was just take an element A, break it up, break those terms up, break those terms up. Eventually you get an almost unique product of irreducibles. All right, wonderful.